All right, going to get started at the good old 8:05. And yesterday we found out that there's been this chunk of information that we didn't know about graphing hyperbolas when we came out of Algebra 2. And that big chunk has to do with slant asymptotes. So something we didn't know existed, which now we do, and we can add that to our toolbox of things that we know how to do with hyperbolas. And so we began by just introducing that and saying, okay, slant asymptotes, when is that going to happen? Well, that happens when we don't have a horizontal asymptote. And today we're going to look at a couple of other times where maybe if you miss something, you might be able to catch it anyway because of what we know about slant asymptotes. So this problem that we had started had us graphing a hyperbola, and we found the asymptotes, the verticals, were at x equals plus or minus 3. And then because of what was going on with the degrees, if we put infinity in here for x in both of these positions, 9 is spitting in the ocean and it's not going to do anything. So we would have had infinity cubed over infinity squared, which simplifies to infinity. And infinity doesn't stop. It doesn't approach a number. And so it doesn't get a horizontal asymptote. So in that case, we're looking for something else that will guide us when we're graphing this hyperbola. And that comes from what we started with, which would have been the division. And like I said, it's a good habit to get into doing long division, even if you can do synthetic division for these. And then what we find is just the quotient piece of our answer when we do that long division is our slant asymptote. So in this case, it was y equals x. Had all of that graphed on there, and then the doggone bell was going to cut me off again. I know we don't have a bell, but we're supposed to let you go at a certain time. So with this one, we're now at the point where we say, all right, we've got a cubic and a squared. Those are not just linear factors. It's going to take us a while if we try to put numbers into this. And so this is the point where we'd say, well, let's make a table, but then let's use the graphing calculator to get the numbers for the table. So with these, what we'll want to do is make tables to represent each portion of the graph. And what I mean by portion is, remember those vertical asymptotes, they don't ever get crossed. So this one's going to have something happening to the left, something in the middle, and something to the right. So my tables should represent that. Now, when we get to the analysis stage, what we'll do is we'll actually try to find a few points on our own first, and those would be the x and y intercepts. So remember from yesterday that the x-intercepts come from when y would be 0. Now, this is y. So I think, okay, what would I have to get on the other side so that this would be 0? Well, I'd have to get a 0 in the numerator, because a 0 in the denominator we can't do. But a 0 on the top, that's going to be 0. So that would give me 0, 0. Oops, wrote it in the wrong one. Getting ahead of myself here. The y-intercept is what we get when we put a 0 in for x. And it turns out with this one, if we put a 0 in for x, we're still going to get 0, 0. So this is definitely going to be a point on our graph at 0, 0. And you realize, wait a second, that's touching that slant asymptote. Yes, slant asymptotes have that same property that horizontal asymptotes have, which means slant asymptotes tell us about the behavior as we go to the left forever and we go to the right forever. But yes, we may actually cross a slant asymptote for the middle portion of our graph. So like I said, now we grab a graphing calculator. Give you a second here to grab one if you don't have one already. Pardon me. And we would punch this in. I'm going to turn the rest of these off. Whoops. There we go. So the only one that's going to graph for me is the one that we want to see right now. And you're going to notice that I use parentheses for the denominator. Now that's really important because whenever we need the calculator to know, hey, there's more than one term in the numerator or one term in the denominator, then we have to use parentheses to let it know. Hey, all of this stuff on the top, do that first. All of this stuff on the bottom, do that second. Now do the division. And in order for the calculator to understand that order of operations, those parentheses have to be there. So notice how in the one that we're going to do right now, I didn't need parentheses for x cubed. Now I could have put them in, better safe than sorry. So if you always want to use parentheses for the numerator and always use parentheses for the denominator, you will always be safe. But with these others, I have at least two terms in each of these, so that requires parentheses for the calculator to do it correctly. Going to try some Zoom 6. Well, look at that interesting thing. All right, so then we're going to need some numbers for our table, and we think about what numbers would be good, and we realize, well, if this was at -3, I'm probably going to want -4 and -5. Because I want something really close to that, but to the left. And then for the middle portion, if I put in -2, -1, 1, and 2, I'll have the entire look for that portion of the graph. And then anything to the right of 3, so 4 and 5 would be good. And I go to my calculator and use the table feature and look up those numbers and write them down. So I'm going to have to do this this way. I'll have it in my hand. Otherwise, I'm not going to get all those numbers. I suppose I could call on people to tell me what those are. But reminder that we typically go to 3 decimal places as well. So let's see, I will put it into my handheld so I have something to look at while we're going through this. So my -4 and -5. -4 is -9.143. That's going to be impossible for you to read. Hopefully you wrote it down. -9.143. -5 is -7.813. This marker is really thick. It makes it hard to do that. And then at -2 we have 1.6. I think I can write that so you can see it. A -1 is 0.125. +1 is -0.125. And 2 is -1.6. 4 is 9.143. And 5 is 7.813. So hopefully with the numbers there, you notice that there's a little bit of symmetry going on. So let's get that graphed. -5 was -7.813. -4 was -9.143. Using the asymptotes. Now later on, after we do today and tomorrow's lesson, we would say, you know what, I really need to know where the highest point for this is. So we would also figure out where the maximum is. That's not what this problem is about. This problem is about us learning slant asymptotes. So I'm not going to worry about that right now. And then we had -2, 1.6. -1, 0.125. 0, 0, of course, which we already knew. 1, -0.125. 2, negative 1.6. And then jumping over to the right side of x equals 3, we have 4 at 9.143. And 5 at 7.813. All right, and then if you get back to your graph, you remember, oh yeah, this is getting closer and closer to my asymptotes, but is never going to touch them. Now, on a test, if we give you a negative 10 to 10 field, we want to see that graph from negative 10 to 10. So don't just make something teeny here in the middle. You want to show us that you understand what asymptotes are there for. So our vertical asymptotes are really working for the middle portion of this graph to show us the behavior. And then our slant asymptotes, those are always going to be for the branches, because slant asymptotes, remember, are behavior as you go left and right forever. So down here at the bottom, they're going to ask us some questions about this. And I want to make sure we did everything we were supposed to do with this graph. It said find the asymptotes and the intercepts and graph the function. We have all of that on there. And what type of asymptotes did we find? We had a couple of verticals, x equals plus or minus 3. We did not have any horizontal asymptotes with this one, but we did have a slant asymptote, which was the line y equals x. So with the star here, it says if the end behavior asymptote is a slanted line, we call that a slant. And then there are some books that use the language oblique. Most of the time you'll hear it talked about as a slant asymptote, so that's the reason that I'm pretty exclusively using slant asymptote as we go through that. But that's the one we find by doing the long division, if the degree of the numerator is greater than the degree of the denominator. So that is the situation when there is no horizontal asymptote. It doesn't exist. And it says, how can you tell what type of end behavior your graph will have? That's what slant asymptotes are for. So use slant asymptotes. And I would just make a note here, to find them, divide. So when the degree of the numerator is greater than the degree of the denominator, divide. You'll be able to find those slant asymptotes. So that's the totally new chunk of information that we're getting here. All the rest of this you saw in Algebra 2. This is just the new piece. So lots of review, but it's been a while, and so it's really good that we are reviewing all these concepts. So now we start where I'm hopeful that we will get through 3 problems today, and that's because each of these is analyze. So analyzing graphs of rational functions, and it says find the intercepts and asymptotes. Use limits to describe the behavior at those vertical asymptotes, so that's why we have this little limit slot down here. And analyze and draw the graph of the rational function. So the analyze piece is all this good stuff down here. So we want to get started with what we would normally do. And normally when I look at a polynomial, the first thing I'm looking at is what's the degree of our numerator and our denominator. So I notice that this is an x to the first, and this is an x squared. Now the reason I'm looking for that is because my go-to place is that denominator. We all know that you can't divide by 0. So if I can factor that denominator, it's going to be much easier for me to find those zeros. But while I'm at it, I could factor my numerator. Don't need to in this case, because my numerator is already linear. But in my denominator, I'm looking for a greatest common monomial factor. There isn't one. It's not a perfect square trinomial because there's a -6 in the back, but very quick and easy to factor that and get x minus 3 and x plus 2. Multiply to -6 and add to -1. Now, like I said, that's where we start. We look at that denominator and say, okay, so if I have zeros down here in the denominator that are not going to cancel out, then I have vertical asymptotes. So my vertical asymptotes are going to be at x equals -2 and x equals 3. And I wrote those down according to the number line, but we'll take those in any direction. If you want to write x equals 3 and then x equals -2, it doesn't matter. So I have the vertical asymptotes done. Now I start thinking about, well, the other asymptotes, horizontal asymptotes. Well, let's see. If I put infinity in here, I have to remember the -1 and the -6 not doing anything. In fact, in this case, because we have infinity squared, infinity raised to a power is so much more powerful than just subtracting an infinity, that in this case, subtracting infinity is going to be dominated by infinity squared. And so we get infinity over infinity squared, which reduces to 1 over infinity, which we know, as we get larger and larger numbers for our denominator, is getting closer and closer to 0. So that would be our horizontal asymptote. Now, they want me to talk about the limits, but they also want me to do the x-intercept and the y-intercept. And before I start scrolling away, I'm going to go ahead and find the x-intercept and the y-intercept, because usually we like to do the limits after we have some of this graphed. So x-intercept is, how do I get my y value to be 0? The only way that y is going to be 0 is if the numerator is 0. If it's 0 over something, then we're going to have 0. So it has to be a 1. That will be an actual point on my graph. Now my y-intercept or intercepts comes from, because we can't have more than one x-intercept and more than one y-intercept, that's going to come from the x being 0 because of the way it graphs. You know, it's 0 something when you graph a y-intercept. So that means what I have to do is put a 0 back in here and see what I get. Well, this would be 0, this would be 0, and this would be 0, so I'm really just left with -1 over -6, which is 1/6. So now at least I know 2 points on my graph. Let's go ahead and get our asymptotes on here. At x equals -2. X equals -2 and x equals 3 and y equals 0. And like yesterday, it might be helpful for you to have, you know, a different color to do the asymptotes with or something, because it really does get hard to see when you are on the x or the y axis there. Now, we know a couple of points. 1, 0 and 0, 1/6. But at this point, we'd want to see, what does it look like? So I will want 3 little tables where I'm figuring out what's happening to the left of -2, what's happening between -2 and 3, and then what is happening to the right of 3. So some numbers here that are to the left of -2, -3, and -4. In the middle there, if we can figure out -1, we already have 0 and we already have 1, and maybe +2, that would give us a really good look at the middle piece of this. And then a 4 and a 5 would do a good job for the right-hand side. So we've got to get this one in the graphing calculator. And again, we have more than one term in the numerator and the denominator, so we're going to need parentheses. So go ahead and get that one punched in, and I'll punch it into my handheld so that I have a table accessible to me as well. And then a zoom 6. looks like so. And using my table, I could check my asymptotes and make sure there's an error message in my table at -2, which there is, and at +3. So that's a good check for your asymptotes. But now we need to start writing some stuff down. So let me get back in here. And at -3, we have, it's -2/3. The calculator's rounding, but you can do decimals or fractions, totally up to you. If you want to always do decimals, that's fine. In fact, I'll just model that for you. And -4 is -0.357. So there's a part for our branch. And then -1 gives us 0.5. 2 gives us -0.25. Down to 4, and 4 is 0.5. And 5 is 0.826 with rounding. 286. I think I transposed those numbers there. 0.286. All right, let's get them graphed. Again, make sure you're using the -10 to 10. Fill it in. Make sure that you're showing your understanding of asymptotes by showing that your curves are getting closer and closer to the x equals -2 and the x equals 3 in this case to your vertical asymptotes, but they're never going to touch it. And there it is, all nicely graphed. So now that we have it graphed, it's going to be much easier to talk about what's happening at those vertical asymptotes. So the limit as x approaches -2 from the left, and was this an f of x? I think we're working with strictly f of x's today. Yes. The limit as x approaches -2 from the right. And then we'll do the same thing for 3. Limit as x approaches 3 from the left. And limit as x approaches 3 from the right. Now again, you have to think, what is my blue graph doing as it's approaching those vertical asymptotes? So coming in from the left towards -2, hands going down. -infinity. Here's where it feels really weird because we usually read left to right, but when we're talking about vertical asymptotes, this is saying as we approach -2 from the right. So as I'm coming to the right, I am going to be going up, which is infinity. And then the 3 from the left going down. The 3 from the right going up. And so we have our limits for our vertical asymptotes there. But we're not done because we also have to do all the analysis. But once we have it graphed, then things are going to go pretty quickly for the rest of this. So our domain piece, there are 2 numbers we know we have to leave out. And that's our -2 and our 3. So we'll be going on the number line from -infinity. We're going to hit -2. We have to jump over it and get back on the number line. We're going to go to 3. We're going to have to jump over it and go back on the number line to infinity. Our range. Well, we can see the middle portion of our graph is going up and down forever. So that's going to be all real numbers, which is -infinity to infinity. And a reminder, we do say this is continuous, even though we know we have to lift our pencil to do this, because in order to do certain math at the calculus level, we want to describe them all at continuous, but we have to tell people, except here. So this will be all x's not equal to -2 and x's not equal to 3. Now that not equal is important because we're saying the graph doesn't exist at those spots. Increasing and decreasing. This is where I want to remind everybody that increasing and decreasing never uses the square brackets, and we also can't use the union notation with increasing and decreasing. So let's look at our graph. Increasing and decreasing is always left to right. So this is decreasing, this is decreasing, and this is decreasing. Hey, they're all decreasing. Let's just circle decreasing. But we have to tell them what the intervals are for that decreasing. Pardon me. So the first interval would be from -infinity up to -2. And then remember we had to stop there. I better take a drink before I have a coughing fit here. And I know it's bothered some of you in the past not to have anything between the two, so you're like, I think I'm going to put a U there since there's nothing there. Don't do that. They're not unions. Put a comma if you need to, if that drives you bonkers. Well, we're also decreasing from that middle portion, which is -2 to 3, and then on the other side of 3, we're also decreasing. So 3 to infinity. All right. The next question is symmetry. And remember, we only get two types at this level. It's either even, where it would reflect over the y-axis, or it's odd, which means it's going to be 180-degree rotational symmetry. And I think we can see with this one, because our asymptotes were at -2 and at +3, that's not going to happen. So this is a none. We already said that our range was from -infinity to infinity, so this isn't bounded. That's a no. Local extrema, meaning local mins and local maxes. No, we didn't have any turning points here, so they were just all decreasing, so this is none. But end behavior we definitely can describe. So limit as x approaches -infinity for f of x, and the limit as x approaches +infinity for f of x. And we talked about this before, that when there is a horizontal asymptote, this is what it's for. It's to tell us that end behavior as you go to the left and right. And we did have a horizontal asymptote, and it was 0. Whew! All right, now on the next two, which I hope we can get through, two more, I'm going to ask you to help me out a lot more with this. But I wanted to get through at least one of these where we were talking through all of these pieces before I start asking you questions. So now I think we've learned a pretty good chunk of info and we're able to do that. This says analyzing the graph of a rational function, and you say, wait a second, we just did that. Well, remember, there are infinite amount of polynomials, so there are an infinite amount of cases for us here. Find the intercepts, analyze, and draw the graph of the rational function. Yep. All right, so I'm looking at it and thinking, here's a degree 2, and here's a degree 2. Hey, I might be able to factor both of those. Let's give it a try. So in the numerator, we can take a greatest common monomial factor out. And then in the denominator, we notice it's a difference of 2 squares. But hopefully we also noticed we're not done with that numerator, because that will factor as a difference of 2 squares again. So now I'm looking to see if anything will cancel. And that's because, remember, anything that cancels is going to provide a hole. But nothing's going to cancel. So I'll go to my vertical asymptotes and horizontal asymptotes right away. So my vertical asymptotes are the zeros of the denominator, plus and minus 2. A little faster to write that one is x equals plus and minus 2. And then my horizontal asymptote, remember, these were both degree 2. So if we had 2 infinity squared over infinity squared, because we know that subtracting 2 and subtracting 4 is spitting in the ocean, we don't need that, these infinity squareds would cancel out. And that's going to leave us with y equals 2. That is our horizontal asymptote. Now let's find a couple of points that would be in our graph. So x-intercepts. X-intercepts come from y being 0. But that has to be in the numerator. It's the only way that can happen. So I'm going to go over here to my factored form and figure out I have 2 of them this time. -1 and +1 will do that. So I get 2 x-intercepts. My y-intercept comes from what happens when I put a 0 in for x. So this will be 0 and this will be 0 because they have x's in them. So I'll have -2 over -4, which will reduce to 1/2. There's my y-intercept. Now, I get down to the limits and I think, you know what, I'd rather graph it first. I'd rather have a peek at what's going on. So, label my x and y axis and get my vertical asymptotes and my horizontal asymptote on here. And I see definitely going to have 3 distinct portions of this graph since we can never cross those vertical asymptotes. So let's go put our x-intercepts and our y-intercepts on the graph so we have some easy points that we could do with our head here. -1, 0, and 1, 0. Oops. And then 0, 1/2. But so far that's it. So I have to put this in my graphing calculator. And I'll put that in my handheld as well while you're punching it in. Zoom 6, because we want to see that -2 to 2. Well, that meant that this matches what we had in our -10 to 10 window. This little piece right here, we expected to see that. We can see where the branches are. We can check our vertical asymptotes. We have an error at -2 and +2. And then we could use our table to write down some points that we want to graph. So to the left of -2, -3 and -4 would be good choices. In the middle, we really don't need anything. We already saw what's going to happen, and it makes perfect sense with our asymptotes. So we can just put that one right in there. Don't need that one. The one to the right, though, we're going to need some more points. So we go to the table and we look up -3, and we see that it is 3.2. -4 is 2.5. +3 is 3.2. And +4 is 2.5. It's a nice little symmetry we notice there because we're getting those same numbers back. We graph it. Making sure we're filling that window from -10 to 10. You don't have to go all the way to -10, but fill it up pretty good. We gave you the space because we want to see everything in that space. looks like so. Now we can write our limits as we approach those vertical asymptotes. So the limit as we approach -2 from the left. The limit as we approach -2 from the right. The limit as we approach +2 from the left. And the limit as we approach +2 from the right. But this time I want your help with this. So fill in those blanks. And somebody please unmute and give me the limits for -2 from the left and the right, please.
Positive infinity.
Going up. -2 from the right.
Negative infinity.
It is. Going down. How about +2 from the left? +2 from the right. Positive infinity. There we go. So those are about that backwards thinking whenever you have to come in from the right. And that, like I said, it bothers some people. But if you just slow down a little bit when you're doing those limits, you'll be okay. Alrighty. Domain. Somebody unmute and tell me what we should put for domain. Please.
Negative.
Oh, come on. You were in stereo for a second. Keep going.
Negative infinity to 2, union, and then, or -2, and then union to -2 to 2, another union, and 2 to infinity.
Good. So it seems like I should have given you time to write your answers down first before I asked. I will do that in the future. So the next one. This is a little tougher, so I'm going to show this one to you because we have a problem with this graph. We're not using all the y's. There's some y's right in here that we never get to. So what I have to know is, and I have to know this for certain, that this is the highest y that I have for this portion of the graph, for that interval. So I better get Blinky working and make sure that Blinky tells me that that 0, 1/2 that I had there was actually the maximum. Because remember, this part we can't do without knowing calculus, so we have to ask the graphing calculator for help. So you look at the x and you go, hang on a second, that was supposed to be 0. But again, this is scientific notation, so the calculator is apologizing for not getting you perfectly 0, but it got you 8.2372 times 10 to the -7th, which would be 1, 2, 3, 4, 5, 6, 8, 2, 3, blah, blah, blah. That's 0 for us. I mean, we're rounding to thousandths position. So 0 and 1/2 definitely is going to be where we're at. So negative infinity, because our arrows show we're going down forever, but we do know it's going to stop at 1/2, and that is the highest point, so that's going to need some square brackets on it. Union with, Okay, well, there's a jump here. So there's no y values until I get, oh, that's right, it's going to approach my horizontal asymptote, but it's never going to touch it. So my next cutoff is 2. But I don't include the 2 because remember that was a horizontal asymptote. Okay, we have to say it's continuous, but obviously it's not continuous for everything. What 2 numbers are bad?
-2 and +2.
Exactly. Those are out, and that's because those were vertical asymptotes. Now, this one, when I look at the graph, I realize, well, this is increasing, and this is in, till I get up here. Now it's decreasing. And this one is decreasing the whole time. So I have a mixture with this one, so I can't just circle increasing or decreasing with this one. I'm going to have INC, and I'll put my intervals in there, and DEC, and put my intervals in there. So let's go back up to the graph. So this branch is definitely increasing from left to right, and that's negative infinity to negative 2. The middle portion, what looks like a parabola here, that was increasing until we got up to 0 there. So that's going to be from negative 2 to 0. And again, if it bothers you not to have anything between them, put a comma in there and you'll be good. Then our decreasing is from 0 to 2. And 2 to infinity. So never square brackets with increasing and decreasing intervals, and you can't use the union notation. So if you need to, put a couple of commas in there and you'll be fine. All right, take a look at this one, everybody, and I'd like somebody to unmute and tell me if it has some symmetry, and if it does, what kind?
Yes, even symmetry.
It does have even symmetry over the y-axis. We can fold this one over on the y-axis this time and get the exact same thing. So this is even. Boundedness. Unmute, please, and tell me if this is a bounded graph.
No.
Right, it's going up and down forever. So that's a no. Local extrema. Oh yeah, we had to use Blinky for that. We did find a maximum. We found a local max of 1/2 at x equals 0. That was important. We had to know where is that highest y value to talk about our range earlier. And then the end behavior, limit as x approaches negative infinity for f of x equals, limit as x approaches positive infinity for f of x equals. And I know it takes a little bit to write down that notation. But my next question will be, what should we put for those limits?
Two for both of them.
Exactly. Horizontal asymptotes. There it is. That was a very nice graph. We finally got to see something that had a little symmetry in it. But again, we notice this didn't go exactly the same as the previous example, and that's how hyperbolas are. That's why there are complete classes at college about hyperbolic functions. There's so much that you can do with them, and so much that you can create. Alrighty, so this one says analyze and graph, and again I start by looking at the degree, and I see this is an x to the first, and this is an x squared. So I'm not going to be able to factor my numerator unless I could factor out a greatest common monomial factor, and I can't do that here. So we're going to leave that. But in the denominator I have a quadratic, and it looks like a perfect square trinomial. this is x squared and this is 5 squared. And if we multiply those together and double them and get the middle term, it is a perfect square trinomial. So x times 5 is 5x, doubled is 10. That means we can write this as x plus 5, the quantity squared, a binomial squared. And then we go immediately to the vertical asymptotes. Somebody please unmute and tell me vertical asymptote or asymptotes, whichever you think it is. Right. Zeros of the denominator. Now, horizontal asymptote, that's our whole infinity thing. So we'd have 5 infinity, but on the bottom we see we're going to have infinity squared, and that's going to dominate like crazy. So that 5 doesn't matter, and the infinity is going to cancel. And we'll get 1 over infinity, which as we go to the left or the right forever, we're going to be approaching 0. So y equals 0 would be our horizontal asymptote. All right, x-intercept and y-intercept. Well, the x-intercept is what happens when y equals 0, and that comes from the numerator equaling 0. So we actually have to do a little bit of algebra and a little bit of thinking here to find that one. We'll have to subtract 21 from both sides and divide by 5. So negative 21/5. The y-intercepts, those are easier because that's where you make x equal to 0. So you kind of go back and look and say, this will be 0, this will be 0, this will be 0 because we're multiplying by 0. So it'll give me 21/25. So the y-intercept is usually the faster of those two. Well, let's get our vertical asymptote and horizontal asymptote on our graph. Oops. There we go. Just going to graph them backwards. Well, that's interesting. This first one we've had in a while that hasn't had 3 distinct parts to it, but we still have a vertical asymptote to talk about for limits. But we'll need to get that from the graph. And unfortunately, I'm going to run out of time before we can do a good job with that part of it. So this is where I'll have to stop for today, and this will leave us with 2.5 of these to get through tomorrow, which I know we can do based on what we did today. I'm pretty sure we can make that happen. And you will be able to do the second day's homework there, because at this point what we're doing is we're trying to see how do those degrees affect the horizontal asymptote, but many of the steps after that are going to be the same. I would say that when we get to example 9, things get very interesting, but we have a day 3 assignment for the interesting ones. Remember that in that black folder there are those special analyze papers. You might want to start using that even for day 2 for your graphing, so you don't forget something when they ask you to analyze. But that's where we have to end today because my beeper's going to go off here telling me we only have a minute left. Have a good day, everybody.